Okay, 12.1, page 160. We're all there, ready to go? So ANOVA is short for analysis of variance, which is misleading because that's not what we're really doing with it. What we're doing with ANOVA is we're testing to see if you have multiple means, if they're all the same or not. You know how last time we tested if all the proportions were the same, P1 equals P2, maybe up to P4. Now we're testing if means of a number of categories are the same or not. We've done it before with two means, where we did a two-sample t-test. Does this mean equal to that mean or not? But now what if you have 3 categories or 4 categories, and you want to know if all the means are the same? So there's some restrictions up there at the top. I am not going to quiz you. You can expect that all of these apply, and that we're going to assume our population is normally distributed. We're going to assume they have the same variance, and that we have independent samples. I'm not going to ask you to test to see whether or not that's true, so you can go ahead and assume that it is. When it is, we do what's called an ANOVA test. It's one of the easier tests we have in that all you have to do is recognize the claim is about multiple means, and then it's pretty straightforward. So let's look at example 1. Example 1. We have head injury data, which we've seen a couple times this semester. Head injury data from crash test dummies used in small, medium, and large cars. They're measured in what was called HIC, the head injury criterion. And we want to use an alpha equals 0.01 significance level to test the claim that the different car categories have the same mean. And then there's a follow-up question. So how many categories do I have? 3. What do you think my claim is? If they all have the same mean.
mu1 equals mu2 equals
Beautiful. mu1 equals mu2 equals mu3. All of the population means are the same for the 3 categories. And what are we going to write for each one? At least one is different because we don't know which ones are not equal. Maybe 2 of them are. At least one is different. Very similar to what we did last time. So from there, once you realize you have a test about multiple means, that's what tells you to do ANOVA. What we need to do now is to put this information into our lists. And they have to be, each category is a list. So these are written across horizontally, but all of the small cars will be in one list, all the medium cars will be in another list, and all of the large cars will be in your 3rd list. So I'm going to give you a minute to type all those in carefully. Probably the longest part of these problems is typing the numbers in. It's probably longer than writing your conclusions. It sounds like most of you are there. The calculators have gotten quiet. Okay, once you have it all in there, the directions are right up above example 1. We do an ANOVA test. It's in the same place as all of our other tests. You go into stats and tests. You go down and find ANOVA. And then it just wants to know which list to look at. So in this case, we had 3 lists. So if you typed them into list 1, list 2, and list 3, you would tell it to look at those 3 lists. If you had typed them into list 4, 5, and 6, you would tell it to look at those lists, whichever list you happen to use. With commas between them. Everyone finding ANOVA? Typing that in there. What does it give you?
Gives us a F value.
It gives you an F value. It's doing another kind of F test. Remember we did F tests before when we had 2 sample F tests? So it actually does another kind of F test. So it gives us an F, that's our test statistic. What's it give you?
0.397.
Can you say that again? I can hear you.
3.397.
0.397?
Point.
Yeah, 0.397.
0.397. Anyone who did not get this, you probably typed at least one number in wrong. At least one is different. I got a lot of people nodding, which means that probably that's correct. A lot of nods. So if you didn't get that, just make a note to go back and double check that you typed them in right, because that's the idea then. So that's step 1 is to write our 2 hypotheses. Step 2 is to get your test statistic. Step 3,
P-value.
p-value or critical value. We don't do critical values with f-tests because that sheet is very complicated. We don't even give it to you. So we're going to use the p-value method. And what is the p-value?
0.678 or 676.
676, is that what I heard? We agreed, Kirsty? What do I do with that p-value?
Test it against the significance level.
Compare it to the significance level. How does this compare to my significance level, if I could speak?
It's greater.
It's greater than? It's definitely greater than 0.01. So for step 4, I think some of you are still sleeping from this nice long weekend we just had. We know what to do for step 4? Fail to reject H0? I'm sorry, what did you say? Was that you, Hector?
Yeah, I was thinking very significant value.
We already did that. So then because it was bigger, we failed to reject H0. Remember, if it's smaller, we reject H0. But if it's not, we fail to reject H0. And then step 5 then is to write my conclusion. What is my conclusion?
There's no.
We can't say that they are the same. It implies that though. So Evelyn said the conclusions that the means are the same. That is what it appears to be, but we can't actually say that we have proof or that it supports that because we never can support H0. Yes.
There is no significant difference, significant variation between the means.
We could say we don't have evidence of a difference. That would work. So Hector says we don't have evidence of a difference, or you could say significance, I think you said that, of a difference in the means. What would be the more formal conclusion? Following our process that we've had ever since the beginning of chapter 8. If this was my claim here, and this one was our claim, and we failed to reject it,
There's not sufficient evidence to warrant rejection.
beautiful. We don't have evidence to reject the claim that they're all equal. So you could have said this, I would accept this one. Or if you wanted to be more formal, there is insufficient evidence to reject the claim that all means are equal. Either one of those would be fine. But going back to what Evelyn said, it makes it look like all the means are the same. We don't know for sure that they are, but we don't have any evidence to say they aren't. Then there's the follow-up question, which means you have to understand your conclusion. The follow-up is, where to go? Do these data suggest that larger cars are safer? No? Why not?
They're the same.
Yeah, we don't have any evidence of a difference, so how can you say the larger ones are better? If I took 3 people and said they all appear to be the same age, so this one's older, like that wouldn't make sense, right? So they appear to be the same, so that the answer there would be no. All cars appear to be the same. Now, on your calculator, in addition to the F and the p-value, does it give you anything about your x bars in your display? I don't have mine in front of me. I don't think it does. I want to make sure.
No.
No, it doesn't calculate the F statistics and so forth.
Gives
Um,
them
Sorry, what were you saying?
No, it just gives a lot of weird stuff.
A lot of weird stuff, nothing that looks familiar. If I was looking at this sample though, these 3 samples, and I wanted to look at the sample means for each one, like what was the mean of the X's and of the small cars, the medium cars, and the large cars, could I get that information somehow? Yeah, I could do one of our stats to get the mean for each list if I wanted to. And so my guess is that those means aren't identical from my sample. But they're close enough to each other that I can't reject that they're equal. They may not be equal, but it's not different enough. So if you actually looked at those values, you could say maybe the large ones look better, but it's not different enough. Questions on that one? Looking there? Okay, sample 2. Now we have another table on page 161. They're looking at weights of trees. I still want to know how they're weighing these trees. I'm thinking they must be growing them in containers. How else do they weigh a tree, right? But they have weights of trees, and they were given different treatments at different sites. So if you look at the data, some trees were giving nothing, some were given fertilizer, some were given water via irrigation, and some were given both fertilizer and irrigation. And then they weighed all of these trees, and so these are their weights down there. And the question asks us to use a 0.05 significance level to test the claim that the trees have the same mean weight. And then we want to does the follow-up question after that. So what do I want to do?
Plug the data.
I can plug all the data into my calculator. Go ahead, I'll let you do that first, and then I'll worry about writing my claims. I like to write my claims first, but fine, you can use calculator first. How many lists do I have this time? 4 lists, and now they are lined up vertically for us. You have to be careful to read your data to see which way it's lined up. But the none is all one category, the fertilizer is in all another category. Watch your decimals there. Okay, what do I do first for this problem after you type those into your calculator?
Write your claim.
Write my claim, which is what in this case?
mu1 equals mu2.
You stopped, Brian. That's as far as I heard.
Let's keep going.
Okay, let's keep going. How many are there?
We need 3, we need 4.
3 or 4, thank you. He's still in a food coma back there? There's 4 categories, in this case it's mu1 up to mu4, are all equal. This is the claim. So H1 is that at least one is different. So then I'm assuming you've already run your ANOVA test when you were typing that all in. And you should have gotten your test statistic, which was an F. What did we get?
0.359.
0.359?
That's what I got.
No.
No?
Uh-oh, they outvoted you.
Maybe.
I got,
5.731.
yeah.
Yeah.
Oh.
Uh-oh, double check your numbers there, Brian.
Yeah.
You had the claims up there, the points for that. 5.731?
7.3.
Yeah.
I'll put irrigation twice.
Oh, whoops. Hard to be different when you have the same one in there twice, right? That's our test statistic.
P is 0.007.
My p-value is step 3, 007.
Mhm.
Everybody but Brian agrees with that one? Brian's fixing his. And this is definitely less than our alpha? So step 4,
Reject.
reject H0. And my conclusion is,
There's sufficient evidence to reject.
there's sufficient evidence to reject the claim. To reject the claim that all means are equal. What are their words for it? Actual claim?
Same mean weight.
And they all have the same mean? Thank you. But the different treatments have the same mean weight. So we've rejected that they're all the same, which means at least one of them must be different. So they're growing these trees, they're trying to decide, should we water them, should we fertilize them, should we do both, maybe we should do nothing, does it matter? We found that something does matter, because they're not all the same. Okay with up to there? Now there's a follow-up question, and it says, does it appear that the treatment affects the weights of the trees?
Yeah.
Yes, why?
Because if you read the table, they change when you give them any sort of treatment. So it grows with fertilizer, then it goes a little bit more with irrigation, and then
Okay, so I like what you said, except for the reading the table part. Because just looking at the table, it might look like there's a difference, but looking's not enough. So I agree with what you're doing, combined with the actual test, which concluded that we have evidence that there's some difference there.
that was the simple answer is that we have the evidence.
Yes, we have enough evidence, because sometimes the table will look like there's a difference, but then you don't know if it's enough. So similar to the first one, they might have looked different, but there's not enough. So the answer is yes, because we rejected H0. We rejected that they're all the same. So we have evidence of some difference. Everyone okay with that part? And what was the last one? Which one appears best? Is that what it was?
Yeah.
If so, which treatment appears to be best? You could just look at the table and tell which numbers are bigger.
So fertilizer and irrigation.
Yeah, fertilizer and irrigation, which kind of makes sense if you fertilize and water your trees. But if you couldn't tell by looking, what's important is we want to look at the mean for each one of our categories. We actually want to look at the sample mean from each of our categories. How am I going to find those?
One bar stats.
One var stats for each list separately, right? So we have to do one var stats with list 1, one var stats with list 2. I'll let you guys do that for me so we can find all of these means. These are sample means from each one of our lists. .184. Everyone clear what we're doing? One var stats with L1, one var stats with L2, one var stats with L3. 333? 332?
And then 0.164. And the last one's 1.334.
So one more time?
1.334.
1.334. Any questions on where these numbers are coming from? So if you could look at the table, which I think is kind of obvious, you can see the numbers are all bigger in that last category. But if you couldn't tell for sure, if you had really long lists or they were kind of close, this tells you right here which sample mean is the largest. This one is significantly higher than these other guys. This is the mean weight here, the mean weight, the mean weight. This one is much higher than all the rest. So because this one has the highest mean, we know that that's the sample, or that's the population that would have the highest one, that seems to be the best. So this one, number 4, was irrigation and fertilization. Yes.
I'm sorry. So you're still on example 2, right? You're just finding the means for each one?
Yes. Trying to see which one's the highest. You could have done that for this example over here. And you would have had one that was the highest and one that was the lowest. But what do you think would have happened if we would have looked at them? What would have been different? We didn't do it over here. What do you think would have happened if we did it here versus here?
What's the question?
If we had found the sample means on this problem, which I didn't do, if we had found the sample means here, what do you think you would have noticed?
There wouldn't have been much of a difference.
Aha, there wouldn't have been much of a difference. There would have been some difference. One would have been higher, one would have been lower, but they wouldn't be that different from each other to really say, oh, this is the best. So you have to be careful. Just looking at them isn't enough, which is why I like what Kirsty said, but we have to also tie it along with the test. The test says there is a difference here, so definitely that's the best one. Where over here, there wasn't a difference. So even if you had one that was highest, it really wasn't much different than the other ones. So even if I had asked that question here, which one's the best? Your answer was that there isn't any best. They all appear to be the same, which was the same as our follow-up question. Questions? Okay, I'll have you do example 3. The whole thing. See if you can do example 3. So maybe you should decide if it's bigger or smaller before you round it. Is that bigger or smaller than 0.15? How do you know? But if you round it, or what if you don't round it, is the question. Right, that's the thing. If you round it, it ends up being equal. Okay, what's my H0?
Would it be that I release one? Would you put it there?
Put what?
Since the mean is, it says that they do not have the same equal, so it would be, that would go on the bottom right.
Right, so H1 is actually my claim, is what she's saying, because the claim is that tests that the different groups do not all have the same
So
mean.
mu1 is not equal
But we still have to write H0 where they're all equal.
to,
Mu1, how many categories do we have?
3.
3? So H0 is still there. And then for H1, we could either write the words they have here, that they're not all the same. That's the same though as saying at least one is different. I'll write them both up here. Everyone see what Evelyn is saying though, that this one is our claim this time?
Yeah.
So you wouldn't write it as like mu is not equal to mu2 is not equal to.
Yeah, the reason we can't write that, which is tempting, I agree. This says that they're all different from each other, which is different than they're not all the same. Because I think we talked about this last time. If I say all of you are the same age, to prove me wrong, you don't have to show me that every single one of you has a different age than the other person next to you. You just have to find one person who's different. So we don't actually ever write this for our H1. We can write at least one is different, or you could say not all are the same. That'd be an alternative. But you can't actually write that they're all different from each other because that's a little bit too extreme. Because it might be that two of them are the same and only one of them is different. What do we get for F?
3.59.
3.59?
Yeah.
And what about our p-value?
0.045.
0.045? And what do you know? Once again, I forgot to write down my alpha.
0.05.
Thank you. So how does that compare? It's less than? Barely. So we reject the H0? And what is our conclusion?
There is sufficient evidence to support the claim.
Beautiful. There is sufficient evidence to support the claim. Pen's dying. The claim that the different groups do not all have the same meaning. So that's the test. But Susan's prediction was what?
The constant background sound.
So her conclusion was that constant background would be the most effective and would be better than no sound or unpredictable sounds. How do we decide whether or not her prediction is accurate?
One of our stats.
One of our stats again, right? We now know that they're not all the same, so now we need to check to see which one was best. So we need to find the mean for the first group, the mean for the second group, and the mean for the third group. And compare to see which one was best. Yes.
Wait, how did you know that we need to do the main thing? Like how, like what wording showed you that?
Because we rejected H0, and our conclusion is that they are different. So whenever your conclusion is that they're not the same and they are different, that's when you would want to check the means.
So rejected Joe, not there is evidence.
Yes. What do we get for our three means?
First one's 6,
6,
and 4,
4,
and 3.375.
3.375. We agree with Christian?
Yep.
Yeah? So this group had the highest average score, and that group was the constant sound,
So Susan was right.
so she was right. Support Susan's claim. So her prediction appears accurate? Questions? Okay, let's look down our chart here. Our handout, we haven't pulled it out yet today. It's been a while. Page 3. Page 3 of your handout. All there? Right in the top, in the middle of page 3, one-way ANOVA. It talks about all the requirements. But the important part that you might want to underline or highlight is right on the second line down where it says ANOVA, where it says a method of testing equality of 3 or more population means. You see that in the second little paragraph, last sentence? So that's when you use ANOVA, when you have 3 or more means and you're asking if they're equal or not. And then if you read the rest of it, it tells you about degrees of freedom and so forth. But all we really care about is the ANOVA test down there at the bottom. Questions on that? Okay, that's all the new material for the whole semester. We're done. You've now learned it all. Now we just have to pull it out of the brains at the right time. Okay, here's the plan for the rest of today.